I will be demoing symbol table and abstract syntax trees for our compiler using variables 5 benchmark file. We have modified this to include this function which prints an integer. Note that this takes an argument and the main function does not. This is the concrete syntax tree generated by Antler. On this we will perform code propagation, code folding, we will merge nodes, we'll add node information, we'll change node instance types, and we will create the symbol table tree and update the symbol table index for each node. The result looks like this. Note that the type is not the same as the instance type, because for example this would be a variable node, this would be a constant node, this would be a comment node, and so forth. The symbol table tree looks like this. We have one root table for the entire file. Then we see we have function g and main declared in the root. Then we have for g we have a parameter, so we had to create an extra table for the parameters, which is table 2. There is a parameter a is declared. Then the bodies, they have their own table again, just like the main has the table here. The main has a index of 0 because it has no parameter. I will be showing you that code folding is working in our compiler. So I use binary operations 2 and comparisons 2. Binary operations 2 prints 2 times 2 plus 3, which is 10. So we can see here, 2 times 2 plus 3, it changes into a 10 due to code folding. 1 smaller than 2 for comparisons 2. You can see that here, 1 smaller than 2 changes into a 1. I will show you that code propagation is available in our compiler using the variables 5 benchmark file, which we have slightly modified with these two lines. X gets assigned 10, then Y and Z get assigned X, which should use code propagation. Then X get reassigned 5, and Z gets assigned to X, which should not use code propagation. So we see here X equals 10, then Y gets assigned X, but 10 instead, Z gets assigned X, 10 instead, then X gets assigned 5, and Z gets assigned X, and it did not choose to replace it with a 5. I will be showing you how arrays work in our system. On the left we have variables file 3 unmodified. On the right we have the MIPS file generated. So we see the main function is defined here, and then afterwards in our MIPS file we don't see any declaration for the array, which is because we do the declarations of arrays in our backend logic. So we assign the first element of a to 10, we load in the constants 0 and 10 into the address locations, but the reason this is a 12 and not 0 is because we have already defined the array, and we will later see that these will get the locations 0, 4, and 8 because they are defined first. So number 10 is loaded into address space 16, and 16 is later put into 0 because it's the address location that corresponds to the first element of the array. So for 20, 20 is being loaded into address location 24. 24 gets loaded into address location 4 for the second element of the array. Same for 30. 30 goes into address location 32, and then 32 is assigned to address location 1. So that's how the storing of a variable in an array works, and then of a constant in an array. And then we need to obtain the values, so we can just get the values at that 0 location, and then perform the printing logic, which will make it work.
We translate our loop and eval statements by first setting continue and break labels in the nodes. We do this by going over every node in the statement, and when we come across a continue or a break, we set the label we have to jump to. After this we can translate the entire statement. Then we can still come across the continue and the break, of course, and when we come across we can just get the label from the node and jump to to that label. We used Mars to test all our assembly files with the delayed branching turned off. So we first have a branch here for when our condition is true, and then we have an unconditional branch for when it is false. Because of the delayed branching, it shouldn't give any trouble. We have two kinds of symbol table entries. The first one is for arrays and variables. We keep all the necessary information in there. For example, the type and if it's initialized, so we can generate a warning and initialize it to 0. And if it's a constant, so that it's not updated without generating a failure. For functions, we keep an entry for each function name so we can overload. In all these lists, there is for each overloaded function one index. So in index 0, the type, init, and arguments are for the same overloaded function.
I will be showing you how functions work in our compiler using a custom file and its generated output in MIPS. What happens in the custom file? We define a function and we call that function in the main. Our MIPS file is generated and it's done in 3 parts. One data part and then 2 text parts. 2 text parts are because we have one text part for the main and anything before the main. And then the second text part is for all custom functions, so for all function definitions. The reason we have this is because MIPS will read the file from top to bottom, so it will, and this way we can guarantee that it will read the main first. One way we could circumvent this is if we, at the top of the text segment, if we had a jump and link to the main, and then afterwards, at the end of the main, would and do a jump return, and then of course like end the execution. We have not done it that way. We have just done it the way I've described you first, and the execution is as follows. So the MIPS will find the main function, main label, then it performs a jump and link to the print homework function, as we have seen here, and then it will perform the functionality that was defined in the print homework function, and then it will jump and return.
For our memory management, we use a load store strategy. The advantage of this is that we can easily find where the value we need is stored. Also, we don't have to keep track of which registers are used at what point and which we can still use. The disadvantage is of course that the efficiency is not great. We can have like here that we store it and load it immediately after. We allocate a buffer space at the start of the program and save this location into register as 0. We also allocate some frequently used floating point numbers, 0 and 1. The last thing we allocate at the start of the program are parts of strings. By allocating parts of strings, we can simply print the string, then print a value, and then print the rest of the string. For our error handling, we did not change much since the last deadline. We assume that the LLVM translation will happen before the MIPS translation. So while we follow the structure of our LLVM translator in our MIPS translator, we deleted most of the error handling. This is because if an error happens, it will happen in the LLVM translator and the translation will stop. It won't come to the MIPS translation.
I have just generated all the benchmarks. There are a couple that are not working that you can see with these red lines. So that's that. And the reason they are not working is as follows. So we have pointers that are not working. We don't have a function return. For the float to int conversion, we are not really sure what's happening there. And with the variables 8.1, the recursion within arguments of an array is not supported. So we would require the array values to be a constant to the indexes of an array.